Yeah, thank you very much for inviting me to this seminar. I'm really honored by gathering such a crowd of people in this room. I don't remember when I get so many people last time in the room when I give a talk. And I must admit that I give talks here with the interval of almost 50 years. I first was in Sofia in 1975, and now it's 2024, so 49 years ago. Okay, so that was a completely different life, completely different story, a completely different appreciation of mathematics in society, I should say. Okay, so I'm going to talk today about, oh, by the way, Professor Gretzky said that he was my first PhD student, but of course he was almost of the same age as myself, and when he came to Moscow in 1970, what was this?
1976.
Yeah, he was almost ready doctor of sciences, so it was very easy to supervise him. So although he said that he was my first student, that's not exactly 100% true. So, but about 4 generations that I believe, because there are people in Brazil who are his grandchildren and their children.
Yes, they are your grandchildren.
Even more. Okay, so it's very nice to see people here. Some of them I saw, some of you I saw many years ago. And thank you for coming for this talk again. So I'm going to talk about a joint paper with Alexander Olshansky. That was published in the Journal of Algebra. 23. Okay, so that's it's called Nilpotent algebras. Implicit function theory. And polynomial quasigroups. So it's a little bit far from my former students and children of my students do, which is polynomial identities. I will touch upon the polynomial identities a little bit in this paper, but here is the main theme is the connection between different types of algebras. So we know there is the classical stuff, Lie theory. Of course, when we study analytic groups, then there is always a Lie algebra attached to this. So you take a group, take identity element in the group, take tangent space, and on this space you have the operation of commutator, Lie commutator, which makes your tangent space the group. That is a group G. There is identity element in the group. You take E of G, the tangent space. Okay. And the natural way of looking at the vector fields on the manifold, essentially more general. You can always define the commutator of vector fields, and as a result, with any group, and analytic groups or any analytic manifold, actually more general, you can associate the Lie algebra of vector fields. Okay, invariant vector fields. So here you see that the Lie algebra and the group are rather different things. One of them is just a manifold, and the other is a tangent space. So they touch each other only in one point. So my goal of my talk today will be to show that there are situations where the group and its tangent Lie algebra is the same thing. So you can introduce both operations, one of the group operation and the Lie algebra operations, that is a vector space structure and the commutator on the same set. Okay, and that was a topic which was best studied by Anatoly Martsev. And it refers, I think, to 1949. So he showed that if you have a torsion-free nilpotent group, and this group is complete, that is, you have extraction of roots on the group, then the group itself can be made into a Lie algebra. You can introduce the commutator elements starting from the group operation. So you have just a set with one operation, and you want to make it into a Lie algebra. That's very interesting because, first of all, you must make a group into a vector space. And then on this vector space, you must introduce addition and multiplication as derived operation to the group operation. So that's what Martsev noticed. And actually, that is this correspondence, Martsev correspondence, that there is a name used for this. So it was between groups, three important groups. And rational Lie algebras, also important, over Q important Lie algebras over the field of rational numbers. Well, usually that here is complete groups. And all this in the situation where the group is finitely integrated. And the algebra is finite dimension. So Maltzer's theorem says that once you have a complete torsion-free nilpotent groups, then you can make a Lie algebra L of G, which is as a set coincides with the group G. As I said, that this is the same thing. But of course, the group has only one operation, and the algebra has the operation of vector space, addition, of course, and bracket, commutator of elements. Okay, so but this is just the first piece. The thing is that any subgroup here, which is closed on the extraction of roots, complete subgroup, is a subalgebra of the algebra, and the other way around. So subalgebras and complete subgroups are the same thing. Ideals and normal subgroups are the same thing. The homomorphism of a group are the homomorphisms of the algebras. So that's complete categorical equivalence of category of complete important groups, torsion-free, and the algebras which are important and over the field of rational numbers. So the gist of this is that if you have some theorem about groups, then it is actually a theorem about the algebras and the other way around. So some people explored this because this was a long time ago, and people approached this from different sides, but there are still some questions which can be answered using this correspondence. And in this paper, which I'm talking, we just fill more gaps. So there is a way of using Lie algebras for groups. There is a way of using groups for Lie algebras. And we just give three examples in this paper where to get theorem about groups, we use no things about Lie algebras, or from Lie algebras to groups, and also some mixture of these things. Okay, so what actually is how the correspondence between Nilpotent Lie algebras and groups is built? Well, for this, people use the classical stuff, the Baker-Campbell-Hausdorff formula. So the Baker-Campbell-Hausdorff formula, the best way is to start with the free associative algebra. That's the algebra of non-commutative polynomials in some variables. Okay. So just to take any words in the alphabet X and their linear span. Okay, so that's a vector space whose basis is the words. And when you want to multiply two words, you just write one after another. And that is the operation in this algebra. Of course, it's expanded by linearity to the whole set of all the words in this alphabet. So these are words in the alphabet X. We take their span and we get free associative algebra. Okay,
So it's W.
words.
W as what it is.
Span. Span. And the vector space.
I understand, but what is
Words.
X?
W of X is a set of words in the alphabet X.
Roots or
Words.
Something like that.
Okay. So the set of words in the alphabet X becomes
So it's the free monoid, isn't it?
What?
WX is the free monoid
You
generated.
can call it free monoid. I just try to avoid unnecessary words to make it a little more understood for non-specialists. So we have this algebra, and to apply Campbell-Baker formula, we need to complete this linear combination of words to the series. Okay. So instead of looking at finite combinations, you take an infinite combinations. Well, presumably X is a finite set, so there is no problem with convergence of all this stuff. So we can always consider the infinite series of words and their linear combination. So we do the following thing. We take e to the x. So we'll take x and y in x, yeah, and consider the exponent. So just the usual exponential series. Consider just usual exponential series, and then you take e to the x and e to the y. Yeah, multiply this. Well, this you can take the logarithm of this, and you get e to the power of z. Okay, so z becomes a result of operation on x and y, and this operation, as it turns out, it's given by what is called Hausdorff series. So that is a series
which is in terms of x and y, and the operations are addition of this series and bracket. So you don't never consider like x times y, because all monomials that enter into the Hausdorff series are in terms of commutators of x and y. So I would not dare to write the whole general term of the series. It's kind of complicated sum, but the point is that Z is a linear combination of monomials in x and y in terms of Lie operation. Okay, so we can write that Z is x plus y plus 1/2 of xy plus 1/12 of x y y plus another 1/12. So it's always commutators. So that allows you to consider this series as defined on a Lie algebra generated by xy rather than on the associative algebra. So everything which enters here belongs to the Lie algebra generated by the elements xy. And here, why I talk about nilpotent Lie algebras. If the algebra is nilpotent, meaning that the enough many products is equal to 0, I can cut this series. And this will be just a polynomial. So the operation defined by the Hausdorff series is just a polynomial in terms of x and y. Okay? So I just defined my operation z as depending on x and y by this formula. Actually, by this formula, that's implicit function. And then I resolve this implicit function. We have a theorem about implicit functions. I mean, in terms of not just the classical situation of commutative variable, but also non-commutative and even non-associative variables. That's the whole generality in this paper. So we resolve this equation as a function z of xy, and we get the series which expresses the new operation in terms of all operations via the polynomials. So polynomial functions actually are able to define new operations on algebra. That's what is given in Malthus correspondence. If you start with the Lie algebra, actually I do it the other way around. Start with the Lie algebra, introduce operation by this formula, then you can invert this operation. Solve. You know the operation of in group. Then you can express the operation of addition and multiplication in terms of the single group operation. That's called the inversion of the Campbell-Hausdorff series. Not only you can express, so we can write that this operation Z is equal to x circle y. So this circle operation is a new operation on the algebra. But you can express the operations of plus and commutator knowing only this single circle operation. That's called the inversion of the Campbell-Hausdorff formula. So it's also very classical stuff. I don't know whether Mike Wormley is looking to me right now. In one of his papers, there is the computer was used to write the inversion of the Campbell-Hausdorff formula. So if you write something like e to x plus y, yeah, and that is written in terms of some series, say k of e to the x, e to the y, that gives you the way of writing the operation of the Lie algebra x, y through the product in the group. So e to the x, e to the y, elements of the group, but e to the x plus y allows you, by taking logarithm, express x plus y operations through the times operation. Okay, so k of ex e to the y is something like e to the x times e to the y times some group commutators and so on and so forth. So there is one-one correspondence, and it's given by polynomials. So if you take nilpotent Lie algebras, this is only polynomial functions. Okay. So, this Malthus theorem says that once you have any the say torsion-free nilpotent group, how can we apply this technique to arbitrary nilpotent groups rather than to complete? So complete means that the equation x to the n equal to a is solvable. That's complete group. Or sometimes people say divisible group. Divisible group. If this equation is solved uniquely, then it's called uniquely divisible groups. So there are some uniquely divisible groups, and if you just have any torsion-free nilpotent group, you can embed it into a divisible group. So that's one other Malthus theorem, that with any torsion-free group, you can associate what we denote like square root of G. So that's the group such that every power of elements of this bigger group belongs to this group. Okay, so it's kind of extracted roots from this group. And if you have any maps from one of these groups to another, then there is a maps of the roots of these groups. So it's kind of categorical thing. If you can take completion of a group, yeah, then if you have G1 homomorphic G2, then there is square root of G1 to square root of G2. So that's completion. Okay, so with each nilpotent group, you can consider associate a completion of this. Okay? It's a unique up to isomorphism. So it's a complete group, a divisible group, which contains your group G, and every element of this group raised to some power gets into this group. Okay, so typical examples is this. You take UT of NZ. That is the group G. That's upper triangular matrices with integral entries. On the diagonal, you have one. Obviously, this is a group. This is a nilpotent group. What will be the completion of this group? Well, the completion will be, of course, square root of G will be UT of NQ. So this was just a group with integral entries of matrices. These matrix entries are rational numbers, so you can extract roots easily in this group. But every matrix, if you have it, some power of this matrix gets into here. So that's a completion. And that's already, this group can be viewed by Malthus correspondence. So from this group, you can build the structure of the algebra exactly on the same set. Usually what people do, they just forget about the diagonal of the matrix to get nil triangular matrix. And the group Lie algebra will be isomorphic to the Lie algebra built by the Baker-Campbell-Hausdorff correspondence. So you can either take matrices which have 0 on the diagonal, okay, and consider it with the commutator operation. Okay. That's a Lie algebra. And if you introduce the operation by Campbell-Hausdorff formula, you get exactly this one. But you can say that we have operation exactly on the same set. It's just when you do operation, subtract identity matrix, and that will be the result of operation on this algebra. So the group becomes a Lie algebra. This is kind of a real Lie algebra, but this is Lie algebra which appears by Malthus correspondence from the group UT and Q. Okay. So that's only one of the examples of correspondence between groups and Lie algebras. And when I say nilpotent, it kind of sounds like a bad restriction. But the thing is that if you look at this series, then and chop it in some place. That will be a series polynomial on the important algebras of say class C. But if you read one more terms, it will be for the algebras of class C plus one. So these formulas are nicely corresponding. So if you have formulas for all the important classes, then you can recover the series from this formula. So considering nilpotent algebras gives you quite a full picture about correspondence between groups and the Lie algebras. Okay, so that's kind of motivation to what I'm talking about. I really don't know now how much time I left. When did I start? Vitaly, wake up.
You have half an hour.
I cannot see on your slides, these are like.
Certainly.
I started at 30. It's 15.
So, yeah.
I have another 30 minutes. That's better. Okay. So we see that there is a general pattern. If you have an important algebra, then you have an important algebra, say A, and you introduce this algebra with two operations, addition, multiplication, and of course multiplication by the element of the field. Okay, then you can introduce the new operation on this algebra by a polynomial. Well, what does it mean?
You mean nilpotently or nilpotent associative or?
Nothing, just Nilpotent.
Yeah, because.
Not Lie, not associative, it's general. Sure,
Okay.
whatever. So in this paper, it's interesting that the results are very, very general. So we start with the Lie algebras. There is also associative algebras in this pattern, but the result which we have in this paper works for any nilpotent
So
algebra.
that means for any definite words of great length do not exist with this one.
Well, they exist, but they
That
equal to zero.
become zero.
That's right.
This is what I mean.
So nilpotent algebra for any algebra A, is it Lie or nilpotent or it's associative, you can define A to the power of n. What is this? Just take all possible product, and the product now not only product of words, but also brackets. So there are some parentheses.
So we have x, y, z in A. So x, y, z, and x, y, z are not the same element. So that's already true in real algebras, of course. But we consider just all possible words, and on possible words, all possible arrangements of parentheses. Okay, so all possible words with all possible parentheses. So why did I want to talk this? Because my operation, as it appeared here, that is the value of some polynomial. So when we have a polynomial, that's a polynomial of nilpotent algebra, then this polynomial, the value of this polynomial can be considered as a result of operation on the elements x, y. So in order that it works on all possible algebras, not just associative or Lie, we have to consider polynomials which are general polynomials. General, non-associative, non-commutative polynomials. Okay? So what is going to be downstairs?
Professor, is that under the car?
Where? Here, yeah. So we consider now F
X. Okay, and this will be the free algebra. Which means that we consider all possible words, and on these words we put brackets. Okay, so for any element like this one, there is an associative support X, Y, Z, P, U. That's an associative word. But on this word, we can put brackets in several different ways. And people know how to compute the number of brackets, capital numbers, or things like this. Okay, so that's a very big algebra, but what is the advantage of this algebra? If you have any algebra, you can evaluate the elements of this algebra in this A. So if you have f of x, y, z in this algebra f of x, and you consider elements A1, A2, A3 in A, you can always evaluate it. Okay. And the evaluation is just a homomorphism. You take the elements x1, x1, x2, x, y, z here, map them into A1, A2, A3, and this map extends to the homomorphism of f of x into A3. So, and the result of this, the image of element f of x, y, z under this homomorphism is the evaluation. Okay, so every element f, say x1, xn, has degree, defined in the natural way. Okay, so this element has degree 5, this element has degree 3, and if you have that a to c plus 1 equal to 0, but a to the power of c is not 0, then we say that algebra A is a nilpotent of class C. Okay, so that's the algebras we are going to work with. So the algebras where our polynomials live. Of course, the very general, much more general notion than the usual polynomial. But these polynomials have advantage because you can evaluate them in any algebra, whether it's Lie, associative, or anything else. Okay. So now, when we have an algebra A, we can consider the operation. So we just write the polynomial. In this polynomial, we select terms of degree 1. These are terms of degree greater than 1. And we say, we have operation. The new operation is A circle B is equal to A plus B plus something of greater degree. So the operation is actually given on the variables. So this is just a fixed element of the free algebra, but you can plug it into this polynomial, the elements of algebra, and you get the operation. Okay, so that's a general operation of which Campbell-Calder formula is a particular case. One of the other popular operations on the associative algebra, on any associative algebra, you can what is called a circle operation. On any associative algebra, you can use the circle operation. This operation appears when people study, for example, Jacobson radical. Yeah, the circle operation is a popular thing. And it's very easy to see that if algebra is associative, that's also an associative operation. So we get a semigroup with associative operation. But if the algebra is nilpotent, it's also a group. You can write the inverse. So if you have the algebra is not nilpotent, Then there is a problem with writing a to the power of minus one, because it will be an infinite series. But once the algebra is nilpotent, the series stops at some place, and this is a group. So in this way, you can start with associative algebra, you get group. And there are, well, this is a very general thing, okay? So you can get the operation on any algebra, but just writing this formula, but then you have to ask many questions. When this operation is associative,
So here the zero is the unit, right?
zero is the unit inside the group. And but a to the power of minus one, you have to take minus by a plus a squared minus and so on. So you cannot write the inverse for this operation as a finite expression. It will be an infinite expression, but if the algebra is nilpotent, this will be a finite expression. Okay. So you see that there are lots of different operations you can introduce on the same algebra. But if you remember Marx's correspondence, the operations work two ways. You start with the group operation, produce Lie algebra operation. But starting with Lie algebra operations, you could go back to the group operation. So essentially, what happens? You have your algebra A, okay? You introduce the operation by this formula. Okay? So, for example, you have matrices. On the matrices, you have operation plus, product, commutator, and so on. Is it possible to have one operation from which you can produce all other operations? Can you do that or not? So, for example, you take matrices UT of n cubed. Well, let's just take two here. Okay? Maybe three. So you take a group of this kind, and if you have all matrices will look like identity plus some matrix n, which is n is an important matrix, and then you want to recover the operations of addition and multiplication in the algebra, starting with the operation in the group. Can you do it? Recover many operations from a single one? That's an interesting question. What is the best operation from which all other operations follow? Okay, so we give an answer to this question in the following way. I'm sorry. So there is this theorem, which was stated in this paper. Equal way. Equal way. Then F field with at least three elements. Three elements. Then for A Nilpotent plus t greater or equal than 2, the operations a plus b and a times b are derived from this operation star and the scalar multiplication by the elements of F if and only if and here I must divide it a little bit. So my polynomial, this G, the restriction on this G. So G of AB is equal to K AB plus L dA plus M A squared plus N A squared plus terms of higher degree. Okay, so and that's kind of I inserted it in the middle, and even if and only if it refers to these coefficients. You see, that's polynomials of degree starting from 2. So I just wrote the
Because I missed something I didn't see. So this is the star, the star that you mean, the quality star. Okay.
Okay. So I decided to write this operation a little bit in more detail. So that's only linear part. That's start quadratic and third degree and curve. So I decided to write it a little bit more. So the quadratic part, it looks like this. So
And b squared. Sorry, and b squared.
and b squared. There are some restrictions on this K, L, and M, in which cases the operations are not recoverable. I will show you an example. Okay, but in all other situations, you can solve you start with this operation, circle, and express both A plus B and AB in terms of this operation. Okay, so this means that you need to know only one operation on an algebra, and then you are able to recover your original operation. So we can say in terms of mass of correspondence, there is a way of making a group from the algebra, but our theorem, without giving precise exact formula, tells you they can always invert it. Okay, you can always invert it, but what we prove, of course, is much more general, because that was just one of the examples, mass of correspondence. We prove it in much more general situation. Start with any important algebra, take any polynomial operation on this algebra, and impose mild restrictions on the function under which you can recover your original operation.
And this KL can be anything,
KL is just the elements of the field.
I understand, but in particular, can be 0?
That's what I'm going to write right now. Okay. So the restriction is this. They are natural. So if and only if K is not L in all cases, and K is not minus L if M equal to N equal to 0. Okay. Well, let me just show you why these restrictions are meaningful. for example, if you take nilpotent algebra, A nilpotent B, and consider operation A plus B plus A plus AB plus BA. Yeah? Because it's a Lie algebra, AB is equal to negative to BI. It's anti-commutative. So we have the new operation, it's just the old addition. And of course, you cannot recover multiplication if you know only addition on an algebra. So that's a kind of natural restriction you have to impose. Same way, if negative L, you can consider some commutative algebras. And also you get some situations in which you cannot recover your operations of vector space in algebra from the new operations which you introduce on your algebra. Okay, so that's the nature of restrictions. You cannot avoid them, they just appear immediately. So once the restrictions are met, you can always go back from your set with one operation back to the vector space. Well, here actually you must be, it is written that you must use scalar multiplication, which is not quite good. It's not just one operation of product you use. You also must be able to multiply by the elements of the field. But that can be easily avoided if your algebra is anti-commutative, like Lie algebra or some other. Then you don't need to use multiplication by the scalars of the field. You can just use one operation, and from this you recover all the operations of original algebra. Okay, so that's kind of one of the main theorems in this paper. It shows you that you can use multiple correspondence not just on nilpotent algebras, but on much more general situations. And we also show when there is a restriction on this. So now there are some few more words. What kind of set of operations do we get? So once we have this operation, we go from the algebra A to the set with one operation, Q of A, and Q is not accidental because it's a quasi-group. So Q of A with this operation, that what appears on your algebra. Say on the algebra and the polynomial is given by Hausdorff series, you get a group. Okay. So if you have that on the associative algebra, A plus B plus AB, circle operation, you also get a group. But in general, we can claim only one thing, that you can get from your algebra a quasi-group. What is a quasi-group? Well, that's just a set with one binary operation and the equations AX equal to B and X A is equal to B can be solved. There is always left and right inverses for all elements. Then such a set is called a quasi. Well, there is a more restrictive thing, there's a loop. A loop is a quasi-group which gets identity. So this operation not always has identity element. So if this polynomial GAB has no proper powers of variables, like x to the power of 10 is not the term of this GAB. If we do not have such terms, then we always have that 0 is an identity element in this quasi-group. Okay. And if the algebra is anti-commutative, like a Lie algebra, then you get what is called power associative loop. Power associative loop, meaning that the powers of the same x are associated. Okay. So that is in the case where A is the anti-commutative algebra. So there are some general facts referring to many to varieties of algebras. So if A is a relatively free algebra, that is a free in some variety of algebras. So variety of algebras is a set of algebras satisfying some set of equations, polynomial identity. So if A is an algebra which is free in some variety of algebras, relatively free, then Q of A is also free in some variety of quadrigroups. So if you can say relatively Lie algebra, then the Q of A given by the inversion of Campbell-Hausdorff or by the Baker-Campbell-Hausdorff formula will be free in some variety and the other way around. So there is some correspondence between varieties of Lie algebras, Nilpotent, and varieties of groups. Okay, so that's one of the instances. So it's what should I say? It's just the beginning. The idea is that you can use this correspondence to derive results about algebras from quadrigroups and the other way around. So my second part, that is the end of the first part, how you can introduce new operations and what you can do with them. You can invert it. That's the main result of this first part. But the second is how to apply these results to real theorems. Okay, so I don't think I have more time, so I just skip this quickly, 5 minutes. Okay. So one of the most interesting results is about what is called commensurators. Okay. So it's about looking at the automorphism of groups. So if you look at the automorphism of groups, in many cases, they are not sufficient for studying these groups. For example, in algebraic groups, in the paper of Margulis, long time ago, he was considering maps which are called virtual automorphisms. What is a virtual automorphism? So that's a map which is P, virtual automorphism. If there are some groups of finite index, H and K in green, finite index. Okay. And the map P of A into K. Okay, so if you have a group, instead of looking at the automorphism of the group, you should take subgroups of finite index and consider isomorphism between them. On the set of such virtual automorphisms, you can introduce equivalence relation. So if you have P virtual and C virtual, so this is defined on subgroup of finite index H. That is defined on some other finite index. Take their intersection. If they coincide on the intersection, they're equivalent. So the virtual automorphisms form classes, and these equivalence classes are called the elements of the commensurator of the group. Classes and virtual automorphism. So the usual automorphisms, of course, are virtual and therefore naturally embedded. So the automorphism group is naturally embedded in the group of commensurators. You can correctly define the products of these equivalence relations on the virtual automobile, actually the congruence relation. If you multiply them, then they still remain to be equivalent.
Is there a relation between the automobiles and beside the DPC side and the commemorate?
Well, commensurator.
Commensurated to
Well, the thing is that this is a group. Now, in addition to the automobile group of group, we have also the group of commensurators, a bigger group. So your automobile is seen in commensurator. But the main point, which I'm probably right and finish with this, then if you have a group finally generated important, say torsion 3, then you can see the square root of G, which is a divisible group now, and you consider L, the algebra built by the Baker-Control formula. So the thing is that the group of commissurators we prove in this paper, that's isomorphic to the automorphic L square root of G. So you can study automorphism of a group by looking at the automorphism of the Nilpotent algebra, which are much easier thing to do. Okay, so we prove this fact. It's not very difficult, but it's provable. But what is the outcome of this? Because we are automorphism of the algebras, finite dimension. That's an algebraic group. So we see that this group is also an algebraic. Yeah. So you can use all the tools of other theory to apply to the study of commensurators and of automorphisms. Another thing, this is the automorphism of the algebras. They all are linear transformations of finite dimensional space. So each of them is determinant. Now we have determinants for the automorphisms of nilpotent groups. That's also a very nice feature. So lots of things like this. Once you establish this correspondence, you can just use it. Use it to derive the results about the automorphisms of groups, starting with automorphisms of the algebra. Okay. So that's one of the applications of what I told today. It's actually not the applications of general theory which I told, but I just showed you why should we study the connection between nilpotent algebras and quasi-groups and groups, because there are nice applications for this. I also have application in this paper where the results about groups are applied to study Lie algebras. There are so-called filiform nilpotent algebras, which are important in differential geometry, and you can get result of them starting with certain groups of transformations of polynomial mappings. And there is something else which I have no time to talk about, but I wrote you the reference. If you are interested, look into the paper in your book. Thank you very much.
I did that operational power seminar, and the center is very successful because there are about 30 people here, and maybe also about a dozen people online. Do you have any questions or comments? I have only a small comment that there are people who were in the algebras, who were non algebras, and the class of importance is a little bit different. C in your case is for the algebras, but for people like me who use the sausage value with the class C++. But this is not so essential. Okay. Other questions? Okay.
Hi.
Oh, there's someone.
No, you ask.
Yeah. So you told that there is corresponding varieties of algebras and quasi-groups.
Yes.
So how far is it from isomorphism? So I have no idea about the thing, but like I'm wondering if there is an equivalence of these varieties in the.
Oh, I mean the equivalence of, as I explained, on any nilpotent group, a torsion free, you can introduce the structure of the algebras, and if the group was relatively free, then the algebras will be as well. Okay. So it's not I just didn't give you many examples of how actually this works, but I would say that's a good question. We also put a kind of a couple of questions of this kind in this paper.
as an open question. So what kind of varieties do we get from varieties of groups when we apply this curriculum? So it's just the beginning. You're welcome.